Okay, compound angles. So what are we talking about? Well, before we get to what compound angles are, I'm going to derive some things. Here's our unit circle. So a radius of 1. Now there's a point P. I could drop a perpendicular down and get some coordinates of P in terms of the angle there that I've labelled beta. Now using our triangle there, the x value would end up being the cosine of beta. The y value would end up being the sine of beta. So there's our coordinates, cosine beta, sine beta. It does not matter where P is on the circle. It'll always be that. You don't need to worry about negatives because the angle will take care of that. If we're in the second quadrant, for instance over there, let's call that point Q, and say that angle is alpha, then it would still be just cos alpha, sine alpha. Now you might be looking at that and thinking, but hang on, the x value would be negative, but the angle is obtuse, and the cosine of the obtuse angle will give you a negative value. So the parametric coordinates, if you like, of any point on the circle will be the cosine of beta, alpha, whatever you want to call the angle, and the sine. I want to find the distance between these 2 points. So I could do it using trig, cosine rule. So PQ squared will be 1 squared plus 1 squared minus 2 times 1 times 1 cosine of alpha minus beta. That would be the angle in that triangle there. And playing around with that, 2 minus 2 cos alpha minus beta. I could have done it coordinate geometry using the distance formula. So PQ squared would be cos alpha minus cos beta squared plus sine alpha minus sine beta squared. Expand that all out. But you'll notice we've got some cos squareds plus sine squareds, which will tidy up. And we end up with 2 minus 2 cos alpha cos beta minus sine alpha sine beta. Now this is where I lied to you. I actually don't care about the distance between P and Q. I'm actually just interested in these results for PQ squared. They're both PQ squared, so they've got to be the same thing. So 2 minus 2, etc. Well, subtract 2 from both sides, multiply both sides by -1/2, and we get the first of our results. So if I want to expand out cos alpha minus beta, it's not like algebra where we can just say, oh, we'll expand it out. Oh, it's cos alpha minus cos beta. It doesn't work that way. We need to use this formula. Cos alpha cos beta plus sine alpha sine beta. Now, let's replace beta with negative beta. So cos alpha minus beta becomes cos of alpha plus beta. And then we got cos alpha cos negative beta, sine alpha sine negative beta. But now I'm going to take advantage of odd and even functions. Okay, cosine, even function. So that cos negative beta I can replace with cos beta. Sine, odd function. So I can replace the sine negative beta with minus sine beta. And we get cosine of alpha plus beta, cos alpha cos beta, minus sine alpha sine beta. I could sort of combine that into one little formula there. Right, so when it's plus minus, it's minus plus on the other side. Or of course, I could remember it in a much easier way. Alright? It's cos, sine, sine. Right? If it's not the sine, because it's cosine, right? Then it's not the sine. So the sign changes. So all you need to remember is cos, sine, sine. If it's not the sine, it's not a sine. Now I'm going to replace the alpha with 90 minus alpha. So back to our first one, and I get cos of 90 minus alpha minus beta, cos 90 minus alpha cos beta, sine 90 minus alpha sine beta. Well, 90 minus alpha plus beta, let's play with complementary ratios. We get sine of alpha plus beta is sine alpha cos beta, cos alpha sine beta. Let's see what happens when it's negative beta. So we'll replace that beta with a negative beta. And once again, we'll play with odd and even functions. And we get sine alpha minus beta is sine alpha cos beta minus cos alpha sine beta. Or combining it into one. But we get sine cos sine. If it's the sine, then it is the sine. Let's look at tan. So tan is, of course, sine on cos. So I can rewrite my fraction now. Top of the fraction is sine cos sine if it's a sine sine. And the bottom fraction is cos, sine. It's not the sine. We want to simplify this by making it look more complicated. There we go. So we're going to divide everything by cos. Because your cos betas in the first one cancel, and the cos alphas in the second one, and you get a whole heap of sine on cos, tan. So tan alpha plus beta is tan alpha plus tan beta on 1 minus tan alpha tan beta. Well, let's have a look at what happens with the negative. Sub that one in. Tan is an odd function, so replacing that, tan alpha minus beta is tan alpha minus tan beta on 1 plus tan alpha tan beta. Of course, it's much easier just to think about it as tan plus tan on 1 minus tan. Our suite of compound angular formulae, we have sine, cos, sine. If it's the sine, it's the sine. We have cos, sine. If it's not the sine, it's not the sine. And we have tan plus tan on 1 minus tan. Let's use it. So if we wanted to expand this out, and I suppose the first time someone sees something like this, they think of it just like algebra, and as I say, they just go, cos 2 alpha minus cos 3 beta. It doesn't work like algebra. Right. So we go, cos, sine. If it's not the sine, it's not the sine. There's our answer. Simplify this one. Hang on, we don't have exact values for 20 and 10, but look at it closely. It's in the form of tan plus tan on 1 minus tan. Therefore, it's the tan of 20 plus 10. Tan 30 we know, 1 on root 3. Now, what this allows us to do is to come up with exact values for other ratios. Sine of 15. If I can rewrite 15 using the ones that we know, there's lots of different ways we could do it. I could go, which way? 60 minus 45. I could do it as, there's another way, so hang on, 30, 45. So, what way did I go? I went 45 and 30, there you go. So, now, sine, cos, sine. If it's a sine, it's a sine. Substitute in our exact values. And there is the exact value for sine of 15. Root 3 minus 1 on 2 root 2. The mistake people often make with something like this is thinking that alpha and beta are in the same triangle. They're not necessarily. In fact, most times they're not. So when I look at this one and I have to find sine alpha plus beta, I draw up a triangle for the alpha. So it's 2/3 is the ratio. It's the other side, root 5. Draw one up for beta. Root 15 becomes the other side. And now I can simply substitute into sine, cos, sine. If it's the sine, it's the sine. So reading off our triangle, voila. Denominator is 12. 2 plus 5 root 3 on 12. Oh, hang on. The tan of the inverse sine of 2/3 plus the inverse cos of a quarter. Now remember, inverse trig are representing angles. I'm going to let them represent an angle just to remind myself. So I'm going to say, well, alpha is the inverse sine of 2/3. And there's my triangle for that. And beta, inverse cos of a quarter. And there's my triangle for that one. And now I can go tan plus tan on 1 minus tan. Right, let's tidy this fraction up. And eventually, there it is, 2 plus 5 root 3 on root 5 minus 2 root 15. 17D, time for you to play with our new ratios.